Hello everyone, I am Muhammad Jabir and I'll present Chapter 14, Section 14.1, Sliding Mode Control from Dr. Hassan Khalil's Nonlinear Systems book. Sliding Mode Control, as known as SMC, is a robust nonlinear control technique that forces systems' trajectories to predefined surface called the sliding surface. We will have a look at its motivation, key properties, design procedure, and how it addresses its main challenge, chattering. Sliding mode control is widely used because it is robust to matched uncertainties. That means unknown dynamics or disturbances that enter through the same channel as the control input. Another benefit is model order reduction. Once the system is on the sliding surface, the effective dynamics became lower order and easier to handle. In short, sliding mode control helps keep the system stable and predictable, even when the model is not perfect. Let's have a look at this motivating example. Let's consider a second order nonlinear system. x1 dot equals x2, x2 dot equals h of x plus g of x multiplied by u, where g of x is greater than or equal g naught, which is greater than 0. Now we define or design the sliding surface as s equals a1 x1 plus x2 equals 0. When s equals 0, the reduced order dynamics become x1 dot equals minus a1 x1. So x1 goes to 0 exponentially. The control law is u equals minus beta of x multiplied by sine of s, with beta of x chosen large enough to dominate the uncertainty. And afterwards, we will use this candidate Lyapunov function. V of s equals half s squared, and we get v dot equals minus g naught beta naught absolute value of s, which shows that s of t reaches 0 in a finite time. And this simple motivating example illustrates that the two-step idea of the sliding mode control is we first drive the trajectory to the surface and let it slide along it. I know that I have not worked through the mathematics in the slide. I just showed the main idea. I will later on describe the problem and the procedure in a simplified way. The sliding mode phases. Sliding mode control has two distinct phases. Phase 1, reaching phase. Starting away from the surface, the controller drives s of t to 0 in a finite time. And phase 2, the sliding phase. Once s equals 0, the motion stays on the surface and becomes insensitive to matched uncertainties. Keep in mind that the first phase requires the discontinuous control to act strongly, while the second phase delivers the robustness we want. Is that clear? I hope it's clear for you. The main key properties of the sliding mode control are robustness against matched uncertainties, model order reduction on the sliding surface, finite time reachability of the sliding surface, of course thanks to the discontinuous control. These features make sliding mode control ideal for systems needing fast and reliable response under uncertain conditions. We are talking about like aircrafts, robotic arms, DC motors. We will see later on. In real hardware, the ideal sign switching control cannot switch infinitely fast. As a result, near s equals 0, we see a high frequency oscillations called chattering, which is the main problem in sliding mode control. Chattering can cause multiple problems. First, wear or fatigue in mechanical actuators, extra power loss and heating in electrical drives, even loss of stability near the surface. Remedies include combining a continuous term with the switching term or replacing the sine function by a smooth saturation function. What does this mean? The problem can be addressed by combining a continuous term with a switching term or replacing the sine function totally by a smooth saturation function, not a typical saturation function. All right? For example, for a smooth saturation function, assume u equals minus beta of x sat s over epsilon, where epsilon is chosen to be small, defined as a thin boundary layer. Inside that layer, the control becomes smoother, greatly reducing chattering at that boundary layer. Okay? And now let's move on to the general design steps of the sliding mode control. To design a sliding mode control, we follow the following steps. Step 1. Choose the sliding manifold s of x equals 0 so that the reduced order dynamics are stable. Step 2. Design the equivalent control that would keep s equals 0 once reached. Alright? Step 3. Estimate the uncertainty bound q of x. Often we will do that via the Lyapunov analysis, of course. Step 4. Pick the switching control v equals minus beta of x sine of s so that beta of x greater than q of x over g naught. Add a boundary layer if chattering needs to be reduced, which is the fifth step. Following these steps systematically, I ensure the system reaches and stays at the sliding surface while remaining stable. Okay? A few practical notes in the applications. Sliding mode control is robust to matched but not unmatched uncertainties. Despite that limitation, it has been successfully used in many areas: robotics, power converters and drives, mechanical and aerospace systems. In robotics, for precise joint control under changing loads, of course. Speaking of power converters, for voltage or current regulation despite load changes. And in aerospace systems, where robustness to friction and parameter variation is very critical. Okay? To summarize that, sliding mode control achieves robust stabilization, finite time convergence, and model order reduction by keeping system trajectories on a well-designed sliding surface. The main engineering challenge is chattering, which can be mitigated with techniques such as saturation functions or boundary layers. Because of this strength, sliding mode control remains a probable choice for controlling nonlinear and uncertain systems. Before wrapping it up for you, let's take a closer look at why sliding mode control achieves finite time reachability. We pick a Lyapunov candidate function v of s equals half s squared with a control law y equals minus beta of x sine s. We get that beta dot equals ss dot is less than or equal minus g naught b naught of s absolute value. Since v naught is less than 0, where whenever s not equal 0, the energy function v of t decreases to 0 in finite time. This formal proof reassures us that the system will reach the sliding surface regardless of uncertainties as long as the switching gain is chosen properly. I hope you got what I mean. This is like a proof that we reach stability nearby the switching surface. We have already mentioned that chattering is the main challenge, but this slide highlights the boundary layer method. In ideal sliding mode control, the discontinuous sine function causes high frequency switching around s equals 0. This is impractical for physical actuators and can lead to energy loss or component wear. To fix this, I told you we will replace the sine function with a saturation function inside a thin layer near the surface to make it smoother. For example, y equals minus beta of x sine s over epsilon. This means that for a very small s, the control becomes smooth and continuous. Hence, the system will no longer stay exactly on s equals 0, but instead in a narrow band. The absolute value of s is less than or equal epsilon, which will be called as the boundary layer. This compromise trades a tiny steady-state error for a significant reduction in chattering. All right. Finally, let's see a practical application: DC motor position control. Suppose that the motor shaft to follow a desired reference angle despite low torque disturbances. We will define the sliding variable s equals theta dot, and sorry, the dot is like not very clear in this slide. Theta dot plus lambda theta minus theta reference, where lambda tunes the speed of the error correction. The control airbot is chosen to be y equals y equivalent minus k sine of s, where y equivalent maintains the sliding surface and the second term ensures convergence to it. With this sliding mode control law, the motor achieves fast and robust tracking, even the system goes through friction and parameter variations. And this example shows why sliding mode control is so popular in mechatronics. Now we can conclude that sliding mode control not only provides theoretical robustness, but also proves effective in real-world applications like DC motors, robotics, and power converters. That's all for today. Thank you again for your attention, and goodbye.